Okay, I'm going to continue our little discussion of water and HVAC and BTUs and so on related to it. This is a little chart. Some of you may have seen this before. It's kind of HVAC 101 sort of stuff. BTUs are traveling this way. Increase in BTUs going this way. Increase in temperature going this way. Now, I'm going to take a pound of ice and turn it into a pound of steam. In order to do that, I'm going to have to increase its temperature, but I'm also going to have to change it twice, from a solid to a liquid to a gas. Okay, and that's what this whole chart brings up. Let's say I have ice at 0 degrees Fahrenheit. Well, if I want to raise its temperature, all I have to do is add heat to it, and the temperature will raise. You notice this line is angled because this takes BTUs. Now, this isn't a scale or anything, but it's going to take BTUs because it's absorbing sensible heat. So it's going to, that 1 pound of ice is going to absorb heat until 32 degrees, and it's going to absorb heat in amounts that relate to its specific heat. Now, I've told you specific heat of water is 1. It's the highest practical substance out there. But ice is not the same. Ice does not have the same specific heat as water. It's around 1/2 of a degree to increase 1 pound, 1 degree Fahrenheit. Okay, so we start down here and we get up to 32. That's going to take 16 BTUs. When it reaches 32 degrees, it can no longer be ice. To get to 33 degrees, it's got to be water. So, flat line here is absorbing latent heat at 144 BTUs per pound. Okay, that number's right there, 144 BTUs. We have now got water at 32 degrees. Water has a specific heat of 1. Now we're going to raise that temperature, of course another angled line, and we're going to raise it 180 degrees. It's absorbing sensible heat. Once that thing reaches 212 degrees, it can no longer be water as a liquid. It has to be steam. You cannot raise its temperature above 212 until it becomes steam. So it absorbs BTUs. Now this is the big one, 970 BTUs. Took 180 to get it up there of sensible, but it's taking 970 to turn it into steam. That's the big one. Okay, my final temperature here is 230 degrees Fahrenheit. Now, steam has a specific heat too, and it's not the same as water. It runs again around 1/2 a degree per pound to raise its temperature, so it absorbs sensible heat. That would mean it would absorb 9 BTUs to get to 230 degrees. It's 18 degrees higher than the boiling point. So our total ends up with 1,319 degrees, or BTUs, to change 1 pound of water into 1 pound of superheated steam. Now I just said superheated, didn't I? Well, superheat is something we use a lot of in the HVAC industry. Right here at 32 degrees, and if it's turned into water, it's not superheated. Once it starts increasing in temperature, it is superheated. That's called superheat. So this would be superheated water. When I reach 212 and change it all to steam, and then raise this temperature again, now it's superheated steam. So, and superheat's one of the things we use a lot of. Okay, what can we do with this? What uses can we make with this? Now, I've told you earlier that water is a great thing for storing energy. I've got 1,319 BTUs in this steam right here, if I'm comparing it to the 32 or the 0 degrees Fahrenheit that this ice was. So that's all in that gas. All those BTUs are in the gas. And so we use that in HVAC to do things, to absorb heat, to reject heat, do all sorts of things. Mostly we use the latent heat because there's so many BTUs in there without changing the temperature. But there's a chart for this for every substance out there that can be changed into the the 3 stages of a substance. We use water simply because this thing's about water and what we're doing with water. So the next one I'm going to talk about is we're going to talk about steam and its uses, what we can do with steam, why it is valuable to us. And later on I'll talk about why this makes a difference in sizing of equipment. Little teaser. If I wanted something at 0 degrees Fahrenheit and I wanted a product that way, and it came in at, say, 20 degrees Fahrenheit, then I would only have to change its temperature, and it would take sensible heat to change its temperature, and it would take 10 BTUs to get it down to 0 degrees. So I'd have to have a refrigeration system that did 10 degrees. But if that water, or if that substance was liquid water, I would also have to take that 144 BTUs out of it to get it to cool. Anyway, that's it on this one.